And we continue with the theme of geologic time. And we're going to continue on with the theme of Rolling Stone, of course, as well. And so this is Claire Cameron Paterson right here in this magazine cover. And he gave us an idea that changed the world, I guess you could say. He's a hero that you've never heard of, probably. So he actually dealt with meteorites, but he discovered the age of the Earth. It was 4.5 billion years old, and that's what he came up with. And so he gave us absolute time. He gave us absolute age dating and new techniques for looking at this. And he saved the planet. Okay, he didn't completely save the planet, but it helped save the planet. Let me put it that way. So we're going to talk a little bit about meteorites. We're going to talk a little bit about uranium and lead, and what is absolute time, and what is radioactivity, what is a half-life, and how do we obtain these age dates. Well, it started before him, of course, but in order to look at relative time with a context and say, actually, you can't really disprove it, I guess. I guess what I'm looking for is the answer is, how do we substantiate that the relative age dates that we found earlier from the early 1800s all the way into the 1900s would actually be an accurate sort of measure of time. And it took absolute age dates to be able to do that. And so the absolute age dates are not apparent when you look at a rock. And so there were other techniques that were used actually first. And so one of those was, if we have layers of sedimentary rock, one after another, right, with superposition, maybe if we select some sort of standard for what does it take to lay a layer down, how long a time does that take? Well, it doesn't work out, because different depositional environments have different depositional rates. Yeah, deep oceans are very, very slow, whereas rivers and things like that can be relatively rapid, and deltas even more rapid. And so so sedimentation rates aren't going to work. Now, if you also think about it, the ocean is salty, right? And so maybe the oceans hold the key to the age of the Earth as well. So how do the salts get into the ocean? Well, they get weathered away from the rocks on the continents, and so the continents deliver many of those ions into the ocean that make it salty. So all of the calcium, all of the sodium that's in there, and all those ions, right? And so that's, maybe you could just take the saltiness of the rivers and compare it to the saltiness of the ocean. And you would think that might work, but it didn't. And so the reason is because the oceans are actually dynamic as well as what the Earth is. It's dynamic as well. And in the oceans, I think we have already talked some about this, maybe not, but black smokers and things like that, right? In the deep oceans, that actually scrubs out many of these minerals in the ocean. And so the oceans are not quite as salty as they normally would be if you just had rivers flowing in and delivering all those ions. And so ocean salinity didn't work. It was Thomson, Lord Kelvin, who came up with the ideas like, okay, well, I'm familiar, he says, with blacksmiths. And so blacksmiths, you could actually have tongs and take a superheated piece of cast iron, let's say, and you know how it kind of glows red when it's in a forge, and you heat it up really, really hot. Maybe that's like the early Earth, right? And so if the early Earth was this molten mass that eventually cooled and congealed, essentially, it would be slowly cooling through time. So if you measure the temperature and try to back calculate when it started, so from a molten mass to what the temperature is today, we could then estimate what the age of the Earth is by that cooling rate. And that would have maybe worked if the Earth was a solid ball of iron, and it did not work for this situation because it little known to him, he didn't know that we had radioactive elements, and radioactivity itself can actually provide some of the heat that's in the core of the Earth. And so the Earth is much older than what he had estimated. He'd estimated somewhere around 80 million years, I think. We know that it's 4.5 billion years, but we're going to get to why that is. Why do we think it's 4.5 billion years? So what are those ways that we can actually try to figure out exactly how the Earth is there? And it took a couple of chemists who were working on radioactive elements to try to figure this out. It was Henri Becquerel and Marie Curie, who came up with the idea, and that's all through radiation. And eventually we're going to talk about here the uranium-238, lead-206, and then uranium-235, lead-207 decay series. And we have a special mineral that we typically use now. It's zircon that tends to be the one that is most accurate in recording age dates. And so we'll talk about that. And I have to tell you, Claire Paterson, the guy in the first photo, he's a hero. So we're gonna look at his contributions here in just a minute. So here are the guys that first came up with different ways to try to figure out exactly what was going on. It was actually Edmund Halley who came up with the idea that we could check the salinity. And Joly actually, did the calculations on that. He was a chemist, and so Joly did that sort of work. And he has this very famous, he has a very famous quote. He also looked at the sedimentation rates as well. The sediments of the past are many miles in collective thickness, yet the feeble silt of the rivers built them from base to summit. And so that's one of his comments there. These are the guys who would add to some of those first. So Joly is in the middle here, Edmund Halley on the left-hand side. And let me think who that is on the right-hand side. I think that is Lord Kelvin when he was a young man. And so salinity, sedimentation rates, and black body radiation, they call it when molten materials slowly cool. Those are the three who came up with the early techniques. These are the two folks who came up with the idea that radioactivity actually existed to begin with, and then they began to see how radioactivity actually worked. Henri Becquerel and Marie Curie. And so what is radiation? Well, we're surrounded by radiation. You may feel like, oh, are you serious? Yeah, well, of course. Every time that you look at something, you're actually seeing radiation. That's within the visible light spectrum. And we have several types of radiation, in fact, and so we have radio waves. You can dial in your radio and it picks up those waves. It's very sensitive to that bandwidth. Microwaves, of course. Microwaves can actually be emitted and heat up your food, right? And microwaves are also used for telecommunications as well. And then we have the infrared band of radiation as well. That's the heat you feel on your skin from the sun or from, those red lamps that are in cheap motel bathrooms. That sort of radiation provides heat. Okay, so that's infrared. And then there's a visible light spectrum, and then it goes from the visible light spectrum into the ultraviolet. Okay, so if you think about the visible light spectrum, it goes, well, when I was taking art classes when I was in high school, they talked to us about Roy G. Biv, right? So Roy G. Biv is the color spectrum: red, orange, yellow, green, indigo, blue, green, indigo, violet. Okay, so a green, blue, indigo, violet. That's it. And so that's the visible light spectrum. And when you get into ultraviolet, it's slightly shorter wavelengths. And those shorter wavelengths provide us with ultraviolet radiation. There's UVB and UVA radiation, and that's the stuff we have to kind of be careful about, when you're out in the midday sun and so forth, because ultraviolet radiation can cause skin damage. And then finally, you get into the X-ray band, and so the X-rays, as you know, will go through the human body and project, on a photographic screen. You'll be able to see the bones and so forth then. And then lastly, the highest energy ones of all are the gamma rays. And so the gamma rays can go through pretty much about a foot or more of concrete. So they're very, very active types of radiation. That's the bands. If that's the bands, okay, so we talk about waves, really, essentially, when we talk with these sorts of types of radiation. But when we talk about the particles themselves, sometimes we talk about radiation as particles and sometimes as the waves themselves. So I want you to think about gamma rays as something like photons. So if photons are what we see with visible light, gamma rays would be high energy versions of that. And so those are the waves really we talk about there, but the particle itself is a photon. For radiation, we recognize two types of particles. A third type of particle would be the photon then. The alpha particle is the energy that is released in one type of radioactive decay. So in other words, sometimes one element can become another element by giving off a particle spontaneously. and that's called alpha radiation. And it's essentially a helium nucleus. Okay, so two neutrons and two protons are given off spontaneously, let's say, from uranium. Okay, when that occurs, it turns uranium into thorium. It changes the atomic number, it changes the atomic mass. The atomic number goes down by 2, the atomic mass goes down by 4, because neutrons and protons both have an atomic mass of 1. That's the alpha particle. Now, in this diagram, you can actually see where an alpha particle could be stopped by a sheet of paper. Okay, so that is not a super high energy sort of like radiation event, but we can still record it in the mass of the uranium that's in there that will become thorium then. Okay, so you'd have an amount of thorium that would be remaining from that radioactive decay. The beta particle, so alpha, beta, gamma, right? A, B, and C in the Greek alphabet. The beta is a particle that can change from a neutron to a proton. Okay, so and in fact it's given off in radiation as well. And so what that does, it actually increases the atomic number by 1, changing an element, because the atomic number is what makes an element an element. And so the beta radiation raises the atomic number by 1, and it also changes the atomic mass because it has a weight of 1. And so that's a beta radiation. And a sheet of aluminum or aluminum foil would be able to stop beta radiation. And then the gamma rays can go through lead, okay, as you see here. So the 3 types of radiation that we deal with. And so those things occur very commonly in radioactive elements. Now, most elements are not radioactive. There's a handful of them, though, we have to be concerned about, and so that's usually in the uranium series in some way. Here you can see 3 of the series that are listed here. It's the uranium series, the actinium series, and the thorium series. And so with uranium-238 can go to thorium, which goes to I think it's proactinium, actually, is the PA there, and that's through, okay, so uranium to thorium in this diagram on the left-hand side here. Uranium goes to thorium through an alpha decay. It loses 4 particles, and so when it does that, it turns it into thorium, and then the thorium can gain one proton then and become proactinium, and then it gains another one in another beta decay. Oh, actually, it gives off a neutron to become a proton. Anyway, it goes up to uranium-236, I think it is. Anyway, you've lost a couple, and then it goes through this whole. It's a lot like a pachinko machine, if you've ever seen those things. So the balls rattle down and so forth, and you get at the very end something that is not radioactive, and that's uranium-207 in this series. For the uranium-235 series, it's uranium-206 with the uranium-235. And so if you measure the amount of each one of those elements, you can do that with a mass spectrometer. This is what Claire Paterson did. In fact, you can actually get at the amount of decays there have been, and you can calculate based on the theoretical decay constant for each one of these elements how long it's been. Okay, so you have to have a series that contains essentially the original amount of uranium, and then you measure the uranium and the lead, and you can tell how long it's been there essentially. Here's Claire Paterson right here next to his mass spectrometer. And okay, so when he was doing this sort of work, he realized that uranium-238 and 235 had 2 different decay rates. So for uranium-238, the half-life for that is 4.5 billion years. The half-life for uranium-235 is 700 million years. And if you compare the decay curves and how much you get from 235 and 238 and the original amount of uranium that was in there, you have 2 different systems that are operating in the same rock that way. And so that goes to lead-207 and lead-206. And so with both of those systems, if you measure both of those, you can compare them one to the other, and you get what they call a concordia diagram. And the concordia diagram, comparing the 2 decay rates on those 2 species of uranium, will give you the absolute age date then. And so here's an example. This is one from the Funzi belt in Zimbabwe where they did a zircon age date, and you can see the concordia diagram here, and they estimate then the age of this at being 400 or 0.4 billion years old or 400 million years old. So with that in mind, what did Claire Paterson actually do for us? He wanted to find out what the age of the Earth was, and he wanted to measure the rocks that would be able to tell us that. And he knew that, in fact, he was from Caltech here in the United States, and he knew that meteorites actually were formed at the same time as the Earth. Well, many of the meteorites, not all of them, but most of them were formed. The ones that come from the asteroid belt formed in a planet at the same time that the Earth formed. And so if we know the age of a meteorite, then we'd be able to figure out the age of the Earth. So he took a meteorite and he tried to figure out what its age was based on the uranium content in it, the uranium-238 and 235. And so what he did, he took it into the lab and he got just meaningless results. And it's like, what's going on here? There, in fact, in the late 1950s, was too much lead in the environment to be able to measure how much lead was actually left over from the radioactive decays. So he began to try to figure out, how can I actually get an accurate reading on the amount of lead? Because, you know, that meteorite probably wasn't exposed too long to the environmental lead that's around it, right? Now you can clean that meteorite off, right? And so you can scrub it really well, and then you'd have something that would be close. But there's just too much in the atmosphere. Why is there lead in the atmosphere? That's because humans are stupid. Stupid in the sense that we put lead in our gasoline back in the old days. If you look today at the signs in gas stations, you'll see unleaded gas. And it's been that way for about 50 years now, and they still call it unleaded, okay? Because we used to have leaded and unleaded gas. And so leaded gas was applied. They applied lead compounds, liquid lead compounds, into gasoline in order to get the motor to not break down. And essentially what it did, it lubricated the valves. And so in the old days, valves were very soft metals and they would break down very easily. And you'd burn the valves out in a car if you didn't burn leaded gas in it. And so that kept them lubricated and it kept them working, in other words. In 1970, they changed all that, and so they added unleaded gas to the lineup of different products you could buy, and eventually they weaned us off of leaded products back in the 1980s, I think it was, 1970s, I think. But older cars still burned lead in their gas, and so I remember those days. How do you get the lead? How was he going to get the lead out? Well, it took an act of Congress, literally, to change the environment. So he changed the world in many ways. This is Claire Paterson, okay? He testified before Congress in the late 1960s and says, we have to get the lead out of the environment. Otherwise, we're going to spoil the environment. There's lead in the atmosphere, and we know that lead is a very deleterious sort of product for children to breathe. It makes children cognitively impaired. And so what we did, in fact, was with his testimony in Congress in the late 1960s, Congress passed the Clean Air Act of 1970, and that changed the world. And so with the Clean Air Act of 1970 and later the Clean Water Act of 1972, that had nothing to do with lead there, but it changed the way that we view the world. That was a time when there was a lot of political activism. The Vietnam War was coming to a climax. It was really pretty bad back then. And so there were a lot of activists that not only wanted to see an end to the Vietnam War, they also wanted to see an end to the pollution. Believe it or not, the Cuyahoga River, which flows through Cleveland, caught on fire at one point in the late 1960s, early 1970s. It actually burst into flames because people were just dumping junk into the river. And, it was a loose spark, something like that, and the whole river, with enough TCE and different compounds that were flammable, it caught fire. And it was a shame. Pollution was horrible back in the 1960s and 1970s, and we still see some of the results of that all the way into the 2020s, okay? But we cleaned everything up. At least we made our first attempt to clean everything up in the early 1970s. And it's something to be proud of. In fact, your parents were probably a part of this, or at least your grandparents may have been part of this. So those two acts right there changed the world as we know it. Claire Paterson was responsible for testifying before Congress and getting Congress to change the way that they dealt with lead in gasoline and also in paint, because paint had an oxide of lead would give it a white tint base, if you will, and so that white tint base became illegal after that. Today we use things like titanium and a few other compounds to give us a white tint base like that. Titanium doesn't react, but lead does. And so children were eating lead chips from the paints that were in their bedrooms and things like this. And so, yeah, all of that changed because of Claire Paterson. So he's a hero. Not only did he discover the age of the Earth at 4.5 billion years, he also took the lead out of our environment. And he built, in fact, the first clean room. And so it was a clean lab. It actually had positive air pressure in it, which would drive away all of the atmospheric lead that was around. He had the room scrubbed, essentially, and sealed off, okay? So the whole room was sealed off with a positive air pressure to keep all of the environmental lead out of it. He went in with a meteorite, and he came out with an age date based on his mass spectrometer experiments. And the age of the Earth today, as we know it, is 4.5 billion years old. Actually, to be accurate, 4.54 billion years old. Older, actually, than the oldest rocks on Earth, because Earth had a catastrophe early on. We're not going to talk about it much in here, but, you know, the moon was actually a result of an impact that blasted away part of the Earth, and it became part of our moon about 4 billion years ago. So the oldest material, okay, a little bit less than that. Okay, so about 4.4 billion years. That's when that impact occurred. The oldest material on Earth is a zircon crystal, and it is 4.4 billion years old. So it goes all the way back to the earliest sort of impact age, if you will. It's found in Australia, in fact. So what do people look for when they look for absolute age dates now? Well, they look for volcanic ash. That's the most important thing that they can do. The volcanic ash, in fact, commonly has a mineral called zircon in it. It's zirconium silicate mineral, ZrSiO4. It's a little bit related to another mineral called olivine. And it forms very early in the crystallization of a magma, and it seems to lock in all of the original components of the uranium series into it and very slowly decays then. Now they can get remelted and things like that, and so very commonly when people have zircons, you can actually look at the history of the age of that zircon by doing a transect across it. They're so fine scale. It's minute sort of like measurements that they make today. There's an instrument called the shrimp, and the shrimp was able to do scans across an entire single zircon to get the span of ages from when it first formed at the core all the way to where it reacted the last time it got melted into a magma. So it's pretty fascinating sort of studies. They call this sort of work, they call it isotope geochronology, and it's really a radiometric age dating is what they do. It's a very sophisticated sort of system. They do that sort of work at the University of Kansas. At least they've been doing it for decades there. Back when I was a graduate student, I had colleagues who were working on that sort of determinations for uranium, lead, zircon age dates. Today there are new applications for this because remember that igneous rocks will eventually become sediments, and those sediments will get incorporated into sedimentary rocks, especially like sandstones. So sandstones very commonly have a small component of zircon in them. So zircon, that mineral, is really important for determining the age dates of not just ancient igneous rocks, but also some of what they call detrital sedimentary rocks, which we can get where they probably came from, so we can learn more about where they were derived from, what igneous province they were eroded from. It's a fascinating sort of field of study. It's not the focus for our work here, but at the same time, that's how we came up with absolute age dates. Okay, so in the last image here, you can see the relative time scale, which is all the names on here, and the absolute ages, which are off on the sides then, in fact. So it's been scaled on the left-hand side, on the right-hand side of each one of the 4 columns here. Those are absolute age dates that were applied when they found an igneous rock that they could date, either a volcanic ash or some sort of intrusive that they could say, okay, this, you have to make arguments when you do this. And so they came up with age dates. So the key age dates for you, okay, let me put it this way. I'm not going to ask you to memorize this chart by any means. That's not going to happen. But I do want you to remember probably 2 of the eras or the eons within the Precambrian, and that would be the Archean, because the Hadean's just too old. Okay, we don't know of any life forms back in the Hadean, so it's immaterial to us. But the Archean saw the first life forms, and that goes back about 3.5 billion years ago when the first life form showed up, and so the Archean's pretty important to us. And that started about, 4 billion years ago. And then the Proterozoic, and the Proterozoic became a heyday for a certain type of organism. In fact, many organisms first began during the Proterozoic. And we'll talk about those in class here. So the Proterozoic is also important for us. So Archean, Proterozoic, know those 2 terms. And then eventually you're going to see at the very end of the Proterozoic here is a term called the Ediacaran. That's a time period within the Proterozoic. And so the Ediacaran is pretty important, in fact, for as with regard to animals and the evolution of life on this planet. There's a time that you need to remember then, and so that time is at about 542 million years ago. And that's the base of the Cambrian, and that gave us a new organization for life on this planet. And so the Cambrian went all the way through to the end of the Permian with life forms, and then there was a mass extinction, an enormous mass extinction that wiped out pretty much like 95% of the marine fauna on Earth. And so we call that the Paleozoic then. So from Cambrian, Ordovician, Silurian, Devonian. You're going to hear these terms, but the ones I want you to remember are for sure are the Archean, the Proterozoic, the Ediacaran, the Cambrian, and then the Permian. You're going to learn that. And then you're going to hear these other ones spontaneously, but I'm not going to, in lectures and so forth, but I'm not going to require you to remember it. But you will remember the Cambrian because of the Cambrian explosion. You'll remember the Permian or the terminal Permian extinctions at 252 million years ago. It's getting closer to local time, right? And then lastly, the Mesozoic here is the time period when the dinosaurs and mammals evolved, in fact. And so that goes from that 252 all the way up to 66.5 million years ago. And since the last 66.5 million years ago, we've had the Paleogene and the Neogene and the Quaternary evolution of life on this planet, for modern life anyway. That's our geologic timescale. That's the origin. When people first began to look at the rocks, they began to describe these time periods. And when they began to do the absolute age dates, they narrowed in on those sort of like boundaries between these time periods, and they were able to figure out the absolute age dates. Yeah, we'll take it from there next. So we'll go on. We're going to talk a little bit about the structure of the Earth and how things operate on this planet. But yeah, it's pretty important stuff. So stay tuned for that. And then we're going to get into fossils, and then we're going to get into the earliest forms of fossils. So yeah, stay tuned. Talk to you soon. Bye now.